Gael Pillonnet from CEA, so French Atomic Commission. The topic of this presentation is to propose a new hardware platform for implementing neurons using MEMS technology. So in our institute, we try to sense many things inside a nuclear reactor. And here you can see a fusion reactor. And we have to, in some application, to detect some signature from 10 to 100 Hertz with a high temperature environment and high radiation dose. We want to minimize the inspection because it's costly, and to maximize the security of this kind of reactor. The first solution is to put like a fiber, optic fiber or MEMS sensors, and you have a long cable to go to a safe environment where you put the electronics and digital stuff and to have your informations. But in this case, you have a low sensibility. It's high cost, like if you put fiber, it's like tens of euros for one point of sensing. So another possibility is to put the electronics inside the harsh environment. And but the problem is you don't have to access to high temperature electronics. You have some electronics which is possible to put, but at this temperature it's very difficult because electronics is always a story of N and P type, and when the high temperature rise up, you have no the differentiation between N and P. So at the end, you reach the limit of the physics limits. So it's a rock limits. So how to do electronics without electronics? So one of the solutions is to use MEMS. So MEMS, it's a nano relay. So you mimic on and off states of the transistors by using like a small switch. So this kind of switch can do like logic gates, memories, many function, but at the end you have like you are faced to a problem of contacts. So you have to contact some parts, mechanical parts, and at some time you have some reliability issue. So one other approach is emerging is to use a contactless approach. In this way, you use capacitance and you just move some comb drives. And by this way, you can have also some functionality in terms of digital gates. But anyway, in each this kind of solution, you have just building blocks, and it's very bulky. It's a low frequency, so the question arises to say how to be smart with MEMS. So our approach is to say, go to a neuromorphic world and try to interact MEMS sensors with some MEMS, which is now just a neuron. So it's unlock the problem of MEMS because we don't need too much components to do signature detection. So with few MEMS or tens of MEMS, you can detect some signature very easily, which is not the case if you use digital gates. You don't need high-speed operation because the neuron don't have to be very speedy, fast, and it's the MEMS time constant is quite acceptable in this kind of applications. So our motivation is to use the same layer in terms of technology, the same hardware for implementing MEMS neurons. So just a recall of what is neurons in this context, because there are different types of neuron in the literature. Here it's a binary neuron. So you have, for example, 3 inputs. You have some coefficients. You sum all these things, And you apply a nonlinear function here. It's a sine in this implementations. And by this way, you have signals, and by cascading some neurons, you can use it for signature detection. So this is the MEMS architecture that we use and we choose for this first proof of concept. So here you can see so there is the same color. So you have 3 inputs here. You have a movable part here. So this is not fixed. All the color parts are fixed. Okay. So when you apply some voltage, you attract or attract in this direction. So the first things is to sum all the inputs. Then with the output part of this MEMS, we perform the nonlinear function. You will see after that. This is what we build, so experimentally. So it's a 2 inputs binary neurons, but you can put more in if you want. So you have a spring, you have the inputs, outputs here. So it's a differential outputs voltage, but I have no time to explain why. Here you some of the performance of this neuron. So it's tested at very high temperature and high radiation dose. So for some are not super comfortable with radiation, it's more than 10 times that CMOS transistor can handle. So the first thing is to have some coefficients, and after to sum all these things. So what we do, it's we work on quasi-static regime, so we are not at resonant frequency. We apply some voltage on these 3 inputs, and then by some basic equations, so like first Newton law, you can have the results on the position of these movable parts. So this is the first step. So experimentally, you can see here, we raise the inputs, and then the position here is moving, and the final position is the summation and the coefficients. So the coefficient is are encoded in the number of combs you have. Then, in the second phase, you have to apply a nonlinear function for coding your neuron, and we use like a bistable structure to do that. So you can see here, you are here at the last at the end of the first phase, and then you apply the power. So it's a power clock because it's a clock plus power, and we go to one direction. So we amplify the result that we have. So if we go to the right, we amplify to the right, and if we go to the left side, we amplify to the left side. So it's like a sine function at the end. So we sine the previous results that we have. For sure, you have not just only one neurons. You have to drive another neuron, or more than one, in the next layer. So you have to pass through the output of the neuron has to be the input of the next one. So to do that, we encode the position that we have in the first MEMS. We move to the voltage using like a capacitive divider. So the combs move, so it changes the capacitance. And when we change the capacitance, we change the value of this capacitance. And thanks to this capacitive divider, you can change the voltage. And this voltage can be seen by the next neuron. And by this way, you can move your information from one layer to another layer. It's what you see here. So now we have like the final result, which is the sign, and we keep this value, and we have like a voltage. Here is the voltage that we measure at the end of the neuron. So if you have like a 1, you have like a certain voltage, and if you have like a 0, you have another voltage. So you have some differentiation which can be decoded by the next neuron. Right. And the last phase is to move again to the initial condition. So another thing, which is these things operate adiabatically. So it means that we can recover the energy that we put inside the spring. So it can achieve a very low power consumption. So just to conclude, so for conclusion, for the end, so I show you that you can add some voltage inputs with some coefficients using just a MEMS. So it's a simple MEMS. It's, you know, it's a just COM drive. So it's something like what we use for different sensors. So there is no special technology behind. It's very, very simple that you can build very easily. So the weight of the neuron is caused by the combs. So it's a fix. So you have to train your neuron network before. And when you know the weights, you can put the number of weights you need inside the MEMS. The sum is just Newton first law. So this is very easy. There is no power consumption behind. And the sign is just a bistable structure. So it's a very simple operation. So by using quasi-static operation, so you don't need a high Q because you are not at the resonant frequency. So it's very easy to be packaged. We don't need a vacuum. And it's a contactless approach. So there is no contact between the combs. So there is no issue in terms of reliability due to the contacts. And this is the first proof of concept. Concerning the environment that we target, for sure, the low MEMS time constant, because here the resonant frequency of this MEMS is 10 kilohertz. So as we operate at quasi-static regime, we have to take care of that. But you know, as we have to detect something like 100 hertz, we are high enough to operate at reasonably. So we have 1 million of cycling because there is no contact, so there is it's very reliable. We test it experimentally to up to this temperature, but it can go higher than that. And the radiation dose is very high compared to different other technology we have in at home. Just for the scaling, so for sure, if you want to detect a signature, you need a lot of neurons, something like 10 to 100 for basic signature. But here it's scalable because the information is encoded inside a voltage. So the routing between the MEMS is okay. It's manageable. And as for sure, the MEMS is quite bulky because it's a large combs. But as we don't need too much neurons, it's also manageable in a reasonable footprint. And for the first layer, as the input is mechanical, the first neuron is not done as I explained. There is no voltage for the first layer. So the first layer is directly the MEMS, the mechanical inputs. So for the first layer, you have just mechanical inputs, and you have the same bistable structure at the end. So you can do the same thing, and there is no need of electronics. So this is just only MEMS. You have just 4 power clocks which power each layers, and that's all. So there is no electronics, just MEMS. So this is conclude my talk. Thank you for your attention.